Good morning, everybody, and welcome to Astronomy 100. Today is, we're supposed to meet Monday, but because of the holiday, we couldn't meet. And we really have to have at least one meeting. I am preparing a survey, basically, concerning the textbook, because we really need the textbook so that we can gauge where we stand on these things and what we need to do. This should not really prevent us from doing what in terms of other assignments, because there will be homework assignments that are really directly pulled out of the book. So I really need to start assigning those. And today's actually unit deals extensively with calculations. So we really have to know how to do these things and do them. There is only one unit this week, but before I start talking about that, you guys should have received an email from me or a message from me from Canvas yesterday concerning a special session for tomorrow, starting at 9 a.m., dealing with the Stellarium software. The reason why we have to do that is because I know I have not assigned really, I gave it as an optional activity to do the Stellarium activity for week 2. And that was for a purpose. And the purpose was that you guys get familiar with it, you become comfortable with it, because down the road, we will have assignments using that software. Some of you expressed basically a problem with that software, especially those who have Chromebook PCs, and they could not install the software. So they could not use the shortcuts that are in the instructions in there. So the solution was, because there is always a solution to problems like this, to use the web version. But the web version, if you hit the keyboard shortcuts, they don't work, okay? Because you are actually on a website. So what we really need to do then is meet on Thursday, tomorrow at 9 o'clock, to see how we circumvent that. In addition to the fact that some people had actually issues installing it. So the thing with it is, we're going to meet tomorrow at 9 o'clock. It's planned for 2 hours, but most likely it will take less than that, to basically go through the entire thing. This is, as I said, it's an optional meeting, meaning if you already have solved the problem for yourself and did the activity and you're satisfied and you're happy with the software and you know how it works, you really don't need to attend it, and you don't even need to watch it recorded later on. However, if you have an issue with it, or you're not confident 100%, or you're not sure if it's really the way it's supposed to be, it's a good idea you attend. Okay, it's a good idea you attend. There will be no assignment based on that meeting, meaning there will be no participation grade for it, for discussions or anything like that afterwards. But this is the idea behind it. It's really to help you be familiar with it, because down the road, there will be assignments based on this software. And whether you could install it or you can install it or you can't, so it becomes a relevant issue, because in either case, there is always a solution. You can always go to the web and basically launch the website and do the activity with the same basically outcome as the person who has it installed, whether using a Mac or using a Windows. That's for 99% of the time is what you have, unless you happen to have also a Linux machine, in which case also you could, there is actually a Linux version of it. So this is for tomorrow's meeting. So I'm hoping that you guys will show up if you can. The link, I did not send it yet. And that's with a purpose, because in the past, when I send links to meetings like this one, people lose them just before the meeting. And they will be looking for them in the email, and they are buried down several layers in the email. So instead, what I do is you will receive a reminder tomorrow morning at 8 o'clock with a link. It will be fresh then, because the meeting is going to happen an hour later at 9 a.m. So that is basically the plan for it. And hopefully we will I'll see you then. So that's item 1. This week, as you can see, deals with the, let me first of all switch to a student view. Yeah, keep it in this format, that's fine.
I have a question.
Yes.
Are we going to need the key bindings for Stellarium at all?
The key, I don't understand.
The key commands for Stellarium, since they don't work on the web browser.
They're actually an option. Actually, the shortcuts you mean, they're actually an option. If you have it installed, you can use the shortcuts, but if you're not familiar, if you really don't care to use them, you can even not use them on the desktop. So yes, you have the option to use them or not, as long as you know what you're doing, okay? So when it asks you to basically turn the screen toward the west, you can use the mouse actually and scroll down toward the west. And if it asks you, for example, to use the key several times until you get to the west, you can do that. Sometimes it asks you to hit the letter L, for example, several times, 6, 7 times. You could actually do it with the mouse too. And that's basically how the whole thing is. So yes, you have the option, okay? Okay, you may skip that. Okay, so let me share the screen. Let me pull the chat in here. So this is basically the week that we have, week 4. As you clearly see, there is only one unit. And there is a reason for it. This unit is by far probably the most important unit that you're going to have, at least in terms of general laws. So this is something that you really need to remember. And this is something that is going to be tested in several different ways. As part of the discussion today, you will be asked to do something. So that is actually participation grade for it. You will receive for this unit. You will be also quizzed on it. Okay. Separately. You will also have a homework assignment doing calculations. That's why I was asking about the book. So this is 3 already types. In addition to, you'll be having it in exams. So this unit is so important. First of all, it sits by itself in a week. And then also it receives all kinds of evaluations, basically participation, quiz format, homework assignment, and then down the road exam. So, and the exam, I know in the syllabus it says September 13th, but we are at least 1 week behind. So it's going to be moved to September 20th. They said the week of September 20th, not next week, the week after. So that is basically something that actually, I did not send a message to it, but I'm going to send the message once I know exactly, because there is still about 3 or 4 units before we hit the exam that we need to make sure that we have them all fully covered and also understood. So that is basically in terms of this week, okay? I'm going to talk, okay, again, please go through the review for the week. The discussion of this week, namely the recording of today, is going to be posted in the discussion in there. And there will be an item of discussion. I did not say what that item yet, but I will say it clearly. And hopefully, if you are watching it recorded, there will be no confusion exactly what you're supposed to be typing, what you're supposed to be putting in there, okay? What I ask for you to do is make sure you watch the entire recording and take notes. Because if you watch the recording and you're distracted, you're going to miss it. You're going to miss the entire basically point that we're trying to get across. And the whole purpose of the participation, if we were in classroom, you're engaged, you are sitting in the classroom, and I'll ask you even to write stuff and submit it to me, okay? So even if you were in the classroom, I always do things. I make sure that you're, but we are not. So if you're watching this one recorded, you really have to be focused on the recording. Hopefully, not hopefully, you have to take notes of what is being talked about, okay? I just said today there is a prompt, so you know that you're expecting something to be asked for today. So when it's asked, and if you are focused and following, you should be able to see exactly what was asked and the answer to it. So it's not just I'm asking the question and I'm leaving it for you to go and research it. No, we're going to answer the question today of what needs to be done. So that is the point where you can pause the recording and type it at your own leisure, okay? On your notes. And then once the session is over, you go to the discussion and you post it And that's it. And you're done with your participation. That means you're fully engaged with the classroom, at least in terms of this part. There are other stuff that is required in this classroom, namely the reviewing here, the reading the materials in the book. And that's why I was asking about the book, because this stuff is, what I do here is just a summary of the summary, if you wish. So you're still supposed to read. Today is only one unit, it's about 5-6 pages, so it's not really a big deal. So you can do it, very quickly. So that is part of the participation also. You're supposed to do that and you're going to be quizzed. Okay. So let's talk about this unit. I'm going to stop sharing and I'm going to pull the unit itself. And I'm going to share that unit with you guys. And after I do that, I need to put the chat because I need to see what people are saying in here. Okay, anyway. So today's unit is about something extremely important. It happened around the 1600s, the 17th century, okay? And what happened in the 17th century basically dictated what happened in the 18th century, dictated, which basically influenced what happened in the 19th century, which influenced what happened in the 20th century and even today. So the point I'm trying to say is this is a series of events that happened in this order. And if it did not happen in this order, probably we will be behind in where we are right now, okay? See, I'm trying to emphasize the fact that this is important. It has importance in two areas, two critical areas, really, in general, on society, not just in astronomy, in society. And astronomy has always been basically at the front edge of a human, basically, discovery and technology. So that's not new. It has been the case from the past. What Mr. Kepler has formulated based on the observation of Mr. Tycho Brahe and based on the work of Copernicus are three laws. Those three laws are based on observation, based basically for the most part on the data collected by Tycho Brahe, okay? And the three laws that Mr. My demo thing, and here it is. The three laws that Mr. Kepler came up with, of course, they're, like I said, based on observation and based on experimentation, if you wish. They needed a framework. They needed a synthesis. They needed a theory. They needed somebody to come and explain them. Okay. Obviously, anybody can explain anything. Okay. They can come up with all kind of mythical theories and explain things. But that's really what happened in that somebody came up with actually sound physical explanation based on theory. Mr. Newton did. However, if all Mr. Newton did was to explain the work of Mr. Kepler, that is useless. That is as good as anybody else. See now the evolution of the human thought and technology and basically other things. If all he did was to explain the work of Kepler or the laws of Kepler, that is not good enough. Actually, his work, which was a synthesis of what, basically an explanation of what Mr. Kepler did, led to other discoveries. And that is what is required in a theory. So Mr. Newton was asked to explain the three laws of Kepler. He explained them with his theory of universal gravitation. And he said, what Mr. Kepler has found for the planets is true, not just for the planets, but it's true for everything else too. The moon revolving around the Earth, the moons of Jupiter, all of the entire stars going around the center of the galaxy, and so on and so forth. So that is one thing, but that could be argued. Okay. There was another thing that was used to solidify, if you wish, this framework, and that was the prediction of when Halley's Comet is going to return. When Mr. Halley looked at the comet and he said, based on the work of Mr. Kepler and actually the theory of Mr. Newton explaining the work of Mr. Kepler, I think this comet will reappear 76 years from today on such and such date. He gave them even the specific day when it's going to come back. Within a day or two, the comet shows up 76 years later. This is outstanding. This is really amazing. So the theory went beyond. Furthermore, when people discovered Uranus, which was discovered by, we'll talk about it down the road, the thing with it is, its motion was odd for two mathematicians, based on the theory of Newton that explained the work of Kepler. Based on that theory, they thought that, wait a minute, this motion needs something near it in this place. They thought that there is a planet that needs to exist in this specific point in space. Nobody knew about that planet, just based on the mathematics, based on the work of Mr. Newton. And they were independent, by the way. The two mathematicians, one of them in France and one of them in England, they were not working together. So one of them was doing the calculations and he thought, okay, there must be a planet in here to explain how Uranus is. There is a wobble in the motion of Uranus. And he sent it to the British Astronomy, basically the observatory there. The British observatory immediately, basically, they did not really follow up immediately with it. But the French one sent it independently, not knowing what the British one did, to the observatory in Germany. And the Germans looked at the data, so they saw coordinates, so they pointed their telescope in that location, and sure enough, that's the planet Neptune was discovered. Pure mathematics based on the work of Newton. Later on, of course, even the British Society turned their telescopes in there, and sure enough, they found it. So again, you can make predictions, and that is beyond that. So that is really the scientific method at its beauty. It did not end there around the 1800s. And even then, there was a problem with mercury, and people struggled to explain mercury based on the work of Mr. Newton. In the 1900s, early 1900s, Mr. Einstein said, you know what, albeit the work of Newton is great, but there is a better explanation for everything that Mr. Kepler have done, including mercury. And he came up with the general theory of relativity. See how this thing evolved, and it all came from this thing in here. So it's very important to see where things fit. So again, historically, basically, hopefully you're going to read through this unit and see basically the context. Mr. Tycho Brahe was a wealthy man, a Danish man. He went into an island near Denmark, and he built an observatory. At that time, did not have a telescope, but basically using all kinds of visual aids to help him monitor the planets. He collected a wealth of data, a lot of data, and he was very protective of it. But he hired actually Mr. Kepler to help him explain the data. And he was still protective until he passed away, when Mr. Kepler had access to all of the data, and he came up with 3 laws. Okay, so let me explain these 3 laws, and we're going to hit on item 2, which is the properties of the ellipse. For that, I'm going to stop sharing so that you guys can see this in full view. Okay, the first law basically says that the planets orbit the sun in a path that is elliptical. So the dark line in here, the black line in here that you see going around, that is the path of a planet. Where the yellow one is, that is where the sun is. So this path is an elliptical path. It's an ellipse. It has 2 focal points. The sun sits in 1 focal point. I put the sun in here, okay? It doesn't matter which focal point you put, it doesn't matter. That's the same thing. So what is an ellipse? An ellipse is a line or an ensemble of points that have the same distance from 2 points. It's similar to the circle, if you wish, or more general than the circle, because the circle has the same distance from a point, from the center. All the lines have the same distance from 1 point. This one is 2 points, meaning if I take this point and calculate the distance to the yellow one and calculate the distance to the blue one, it's going to be the same thing as any other points in here on the circle, this point in here. It doesn't matter which point you pick up from the circle, you're going to find the same thing, the same distance. Okay, So that is basically by definition what the ellipse is, okay?
I'm not quite following.
Okay. Let me probably better change the cameras and see if I can project it on the other cameras. Hold on. I have to switch cameras in here. Oops, it's still the same camera. Okay, so this is the other camera. And let me see if I can turn it slightly so that you see the entire ellipse. Okay, so if I take, let me pick up a pen in here. This point, okay, and measure this distance and add to it this distance. I'm gonna get a number, correct? So this plus this, the distance from the blue and the distance from the yellow. This is added together and pick up any other point. It doesn't matter. Okay, this point, for example. Let me pick up this point. Okay, take this distance and add to it this distance. This number are going to be the same. Make sense now?
I'm not quite following what an ellipse is. What an ellipsis is.
Okay, this is how I constructed it actually. Okay, you see the string in here has the same length. I'm not changing it. All I'm doing actually is moving my finger around the circle in here, and in doing so, my finger is describing the path of the planet. Is the string changing in length?
No.
So that is basically the whole point. That is how you make an ellipse actually.
So that
in other words, this distance plus this distance is the same everywhere you are on the ellipse. Good.
So what is it used for?
This is the path of the planets on the ellipse. Okay.
The orbits of planets or the path of them?
So the sun is here.
Okay.
And any of these two focal points, I just picked up this one at random. There is no preference of one over the other. And at some point, like in the spring, the Earth will be here. In the winter, the Earth is going to be here. In the this is in the summer actually, June 20th. The Earth will be here. December 20th, the Earth will be here. This is the equinoxes. This is the spring and the fall. Okay. So that's basically, that's the entire season for the Earth as it revolves around the sun. So starting from one point, coming back to the same point is 1 year. Okay.
Okay.
So that is for the Earth. The same thing is true also for all of the other planets. The circle, if I take these two focal points and put them in the same point, will be a circle. Okay. As you guys clearly see, the ellipse is flat from one end and bulged from the other. So it's not like a circle which is perfectly symmetrical. No, this is not. This is actually, it has some sort of a shape that is actually different slightly from the circle. So that is basically the properties of the path of the Earth, or any planet for that matter, as it goes around the sun. Now, the ellipse has two focal points. This is the focus point, and this is a focal point. Some books, they don't call them the plural for it, either foci or foci, it doesn't matter. I think it's both true. The distance between the focal points characterizes how eccentric, we call this eccentricity, how eccentric is the ellipse. If I take them and put them very far away, this will be shrinking further and this will be stretching. If I bring them closer and closer, this will stretch and this will compress. So it will be less eccentric. So the distance from the focal points, between the focal points, is what characterizes the eccentricity of the ellipse. From the perihelion, where the planet is very close from the sun, to the aphelion, this distance from edge to edge is called the major axis, as opposed to the minor axis in here. Okay, so this is the major axis, this is the minor axis. This half of the major axis is called the semi-major axis. Half the minor axis, this is the whole thing is the minor axis, half of it is the semi-minor axis. So this is basically what the characteristics of the path of the planets. They go around in ellipses. Each one of them has an elliptical path where the sun sits in one of the focal points. Okay, so whether it's planet Earth, planet Mars. The problem with this is this picture is exaggerated a lot. For this case of the planets, these two focal points are actually very close from one another. They're not exactly zero. The distance is not exactly zero, but it's very close. As a matter of fact, the two focal points sit in the sun. So if this were the sun, focal point 1 and focal point 2 are inside the sun. Okay, because the sun is a huge structure. So this is exaggerated. This is exaggerated number. Okay, so that is basically the whole thing. Other than that, that is basically his first observation. For most of the planets, since the eccentricity, if the eccentricity was 0, we are inside a circle. If the eccentricity is slightly different than 0, we are less eccentric, basically orbit. But for some of these objects, especially the comets, their orbits are very, very eccentric. They go very far away, they go all the way to the Kuiper belt, and they come back very near the sun, and they go all the way to the Kuiper belt, they come back near the sun. So depending on the object, the eccentricity can be very small, almost 0, like the case of the Earth, to that of an eccentricity which is very high for some objects, especially the comets, okay? Those are the ones that have the high eccentricity. Pluto also have a high enough eccentricity, relatively speaking. Sometimes it even goes inside the orbit of Neptune, but most of the time it's outside of the orbit of Neptune. Mars also has a little bit of higher eccentricity than some of the other planets. But that's the point in here for the path of the planet. So this is law number 1. Law number 2, it says the following: as the planet goes near the star, let me see if I have a different color. I don't have a different color ready. Oh, I think I have a red. Okay, let's say, for example, a planet is in this point today. Okay, if I wait, for example, a month later, it's going to be here. Okay, it's going to pass the perihelion. Okay, so it will go through this arc. This area drawn from an imaginary line, not a real line, from the sun to the planet, and then from the sun to the planet in a new position after 1 month. This area in 1 month, for example, is the same. It doesn't matter where you take it. Let's say, for example, we take it in here and we wait for it a month later. It's going to drive just this arc distance, so that this is the area now it's going to cover. These two areas are the same in size, because this has a higher radius, much bigger radius, but a smaller arc. This one has a smaller radius, but a bigger arc. The two areas are the same. So that is the second law of Kepler. The areas are swept at constant rate, meaning for the same amount of time, the arc, the whole area is the same as this area, meaning that it's going to go fast and then slows down, and then picks up speed, and then goes fast and then slows down until it's going very slow, extremely slow, as a matter of fact, and then starts to pick up speed, and then it goes around. So it's going like this, okay, to cover bigger arcs over the same amount of time as it is in here, which is a smaller arc, but it's a bigger radius. So the areas are the same. So that is the second law of Kepler. The third law of Kepler was a little bit hard to come up with. Actually, he came up with the first two laws. Let me switch cameras quickly. Does this make sense now?
Yes, it makes sense. I get it.
Very good. Okay, very good. Okay, again, you guys know that this is not in lieu of reading the book, okay? So please read it so that you can see these things. And it's nice. It's actually fun to make this ellipse. All I needed was to pin to basically thumbnails and thumb pins or whatever they call them, and then actually strong enough to hold the marker, and then go around the thing to make it. So it's really fun to do. And then you measure the semi-major axis, you measure the semi-minor axis, and you measure actually the distance or half the distance between the focal points, and you do some calculations, and you find the eccentricity of the the eccentricity of the ellipse, which is a critical property of the path. Okay, so let's look at the third law. Third law was a little bit more work to talk about. Let me go back into the same camera because it's important to look at it also there, what's going on. So I have actually another marker in here I can pull. Okay, if I take any time, let's say, for example, the planet is here today. Okay, today is September 8th. September 8th, this is, for example, September 8th, 2021. And if I wait for it, for the planet to go around the sun and come back again, and a year from today is going to come back to September 8th again, okay? That means the planet has taken 1 year. We call this one a period, okay, P, okay? For the Earth, it's exactly 1 year. For Venus and Mercury, it's less than a year because they are closer to the sun than the Earth is. For Mars, it's more than a year. And for the different planets, it's different numbers, okay? And if I call this number A, remember, this whole from here to here is the major axis from the center of symmetry to the perihelion, for example, or the center of symmetry to the aphelion. That is actually the semi-major axis. What the third law says is that this numbers P squared in years is the same thing as A cubed in astronomical units. Okay, it's not showing. That is basically what this third law is. So these are the 3 laws of Kepler. That's actually today's assignment, is to write these 3 laws in your own terms. I'm not done yet, so we still have time. Okay, so we can talk more about this laws. So let me go back into the other camera, and let me, as a matter of fact, share the screen now. Okay, so again, we have the 3 laws of Kepler. Okay, what's the role of Mr. Galileo? Mr. Galileo, remember the story came actually before this too, was the work of Mr. Copernicus. Copernicus basically, when he was asked to fix the calendar, and he looked at the planets, and he noticed that instead of actually the Earth being the center of the solar system, because if you tonight go outside and look at the night sky, you will see everything going up, and then the dome above your head from the east and setting in the west. That's basically what's going on, including the sun in the morning. Actually, it rises in the east and sets in the west. So everything revolves around the Earth. This idea held for thousands of years. People believed that. Actually, they saw that. I mean, you cannot argue with your own eyes. I mean, you see that day in, day out. You can go out and you will see it yourself. Okay, that is one thing. The other thing also is then, okay, the reason why it does that, I can explain that for you. That's basically the idea behind it, is because Earth is the main thing. It's the center of the whole universe, okay? And because the reason why is because basically we are the center of everything. So that's the belief that we have held in that. In addition to the fact that we look at the Earth and we saw it not as perfect. So that's the idea where the circles came in, that the heavens are perfect. Therefore, everything must be going on a circular path, okay? On a circular path. And the Earth is not as perfect because the most perfect shape is the circle. That's basically the idea that we had. But that's why when Mr. Kepler came up with the orbits being elliptical, the idea to some extent was not accepted because of the fact that it has to be circular. What are you talking about? But you cannot argue with data. He was looking at numbers. He was looking at the displacement in the arc distances and so on and so forth. And those, they cannot be circles. They are actually ellipses. That's one thing. And also the point that Mr. Copernicus argued is that the sun is actually the center of everything. To explain among other things, for example, the retrograde motion of Mars and to fix the calendar. Okay, that's the whole purpose of it. But he did not really abandon the idea of circular paths. It was until Mr. Kepler came in when he when he actually, based on the data, argued that the paths are not circular, rather they are elliptical. That's one thing. Mr. Galileo took a toy that the kids were playing with, telescope, which is really two lenses basically with focal distances. The rays come from infinity and they focus to a single point. That's what the lens is. So he took that toy and he turned it towards Jupiter. The first night he noticed 3 objects revolving around Jupiter. Those are the moons that he saw. He saw Europa, Ganymede, and Callisto. The next night, actually, when he turned to it, he saw actually Io. Io has a 42-day cycle around Jupiter, so it goes very fast. So if you don't see it tonight, all you have to do is just wait the next day, and you will see it coming from the other side. That's exactly what happened to Mr. Galileo. So Mr. Galileo's work is critical in here because here he confirms what Mr. Copernicus has argued, that the Earth is not the center of rotation of everything. Here is an example. You have Jupiter with 4 moons revolving around it. So if the Earth is the center of everything and everything must revolve around the Earth, here are 4 different objects that don't revolve around the Earth. They revolve around Jupiter, as opposed to the fact, or at least the idea that they should rotate around the Earth. So that is one thing. That is one thing in support of Mr. Copernicus. The other thing that he did actually also, he turned the telescope. Initially, actually, he looked at the moon with it, and he saw what appears to be dark regions in the moon are nothing but the shadow cast from hills on the moon from the sun. So what you're saying in here is the heavens have to be perfect and the paths have to be circular, and the Earth has only mountains because men sinned, is not really sound. Here is in a case where an object is in the heavens and it has mountains and valleys too. That is the moon. So in a sense, what Mr. Galileo did with his observations is, in addition to his work on the motion and all of that, and the calculation of G, which was really critical for the work of Mr. Newton later on, is the idea that he confirmed both the work of Copernicus, that the Earth is not the center. We're not in a geocentric, basically, universe. At least as far as the solar system is concerned, we are in a heliocentric sense, where the sun is the center of the solar system. That's one thing. Furthermore, forget about this idea that the paths have to be exactly circular, because here is an example based on the idea that men sinned on all of that theory. It's baseless, because here a case where that does not hold true. So that is basically the work of Mr. Galileo. So it's very important to read the unit, and hopefully you guys learn more from these things and do calculations based on that. Again, describe the properties of the ellipse. I already mentioned those properties. You have the 2 focal points. You have the semi-major axis, the semi-minor axis, and the eccentricity. Those are some of the key properties of the ellipse, the path that the planets take around the sun. List Kepler's last 3 laws and carry out calculations. Okay, item 3, the last item we did. So let me stop sharing the screen in here and share the screen, this one. Let me share it, so that we do some calculations based on Kepler's laws. First of all, let me list Kepler's laws, because they're important. It's this one in here. So this is my interpretation of the Kepler's laws. So this is the item of the discussion, by the way, is to list Kepler's laws. Okay, so the first law, planets, or the, okay, orbit, planets orbit the sun in elliptical paths where the sun sits in one of its focal points. You're asking me which focal point, it doesn't matter, okay? Just pick one of the 2. They're symmetrical. So that is law number one. Law number two, it says an imaginary line, okay? The line I drew there is not a real line. There is no highway between the Earth, for example, and the sun, or between Venus and the sun, okay? There is no line stretching there. It's an imaginary line. It's a mathematical line, okay? The imaginary line drawn from the sun to a planet, doesn't matter which, the Earth or any other planet, sweeps equal areas at equal amounts of time. So that is law number two. Law number three is a more mathematical law, although the second one also is. Actually, all of them are. It says basically the square of the period. I'm going to put a big in, put this in capitals, because the period has to be measured in years, not in days or month or seconds as it is supposed to be in metric system. But it has to be measured in this case in years. For the case it's exactly 1 is the same as the cube of the semi-major axis in, this one also has to be measured in a specific unit, and that is the AU. Okay, mathematically we write this expression, p squared equals to a cubed, provided p is in years and a is in AUs. Okay, so this is basically the three laws of Kepler. That is what we're supposed to put today in the discussion item. Okay, so let me pick up a book in here, the book in here. By the way, I looked at this, both of them are the same page. So I'm using the 6th edition. It could, I have also the 5th edition, the same page. So I'm looking at page 95. On page 95, it has several planets, okay? It has several planets. Let me pick up my calculator also, because at some point I really need to do some calculations. Okay, good. Calculator is on. So I'm going to pick up Mercury, or at least Venus, and Mars, to the both of them on the other sides of the Earth. Okay. For Venus, the semi-major axis A is 0.723 astronomical units, AUs. And the period, basically the year on Venus, so that means it's almost 3/4 the distance away from the sun as the Earth is from the sun. That's what that number means, okay? And the period, it's 0.615, slightly more than half a year, slightly more than 6 months, but slightly less than 2/3 of a year. Basically, what is it, 2/3? Third is 4 months, less than 8 months. So it's anywhere between slightly more than 6 and slightly less than 8. So it's about 7 months. So 1 year on Venus is about 7 months on our year. So when we go 7 months, Venus has gone already a whole year in its planet. Okay. And it's in its 2nd year. And we did not even complete the 1st year. We still have 5 months to go. Okay. So that's what this number here means, years. So let's check now, is it true that p squared is equal to a cubed for Venus. Okay. So what we do in this case is, I'm going to stop sharing the screen, but I'm going to, before I do that, let me set it up first. I need to do p squared. So I need to take this number, 0.615, and multiply it by 0.61.5. Whatever I find in here, I need to compare it to a cubed, and a cubed is clearly equal to 0.723 times 0.723 times 0.723. Whatever I find in here, I need to compare the two numbers. Are they the same? That's what this is supposed to be. Okay. So I'm going to stop sharing the screen, and I'm going to share the calculator now. And the calculator, I need to make 0.72, no, 0.615 first. Let's start 0.615 times 0.615. That's the year. I'm getting a number which is 0.378225. I don't care about the 225 because I really have 3 sig figs in here and 3 sig figs in here. So the maximum I retain is 3 sig figs, 3 significant figures, that is. And that is this first 3 is 0.378. So I'm going to go back into the calculator after I get it from the calculator, and I write 0.378. And I'm going to share the screen once I finish the second calculation. Okay. The second one is 0.723 times 0.723 times 0.723. That's what the cube is. Multiply the number 3 times. Again, I have 0.3779. The reason why I dropped the 2 in here, it's because less than 5. When we do rounding, anything more than 5 or 5 is rounded up. Anything less than 5 is rounded down. And this was a 2, so I rounded down and ignored anything after that. The same thing. In here, I have 3 significant figures, so I need 3 significant figures, but I have to look at this number. I don't care about the others after it. I care only about this number. Is this number 5 or more? It is more than 5. It's 5 or more, actually. Since that's the case, then I have to round it up. Okay, I have to round it up and make this one an 8 instead. So it's going to be 0.378. So it's 0.378. Again, the reason why we do that is because I started with this known numbers. I cannot know more than these 3 numbers. So if somebody tells me this is the answer, well, they are wrong because of the fact that I start with 3 digits. That's the maximum I know about it. You cannot invent more because that's what the measurements were. You cannot, the calculator will going to give you different numbers, and those numbers are misleading. It tells you as if you know all of this for certainty, and you don't. This is what you know for certain. So the maximum you know for certain is just 3 digits in here. Same thing in here. I cannot include this 3 numbers because then it makes the assumption as if I know the answer with that much accuracy. This is not true. I know it only with 3 significant figures. So the same thing has to be true in here too. So I'm going to share now the answers. And lo and behold, the 2 answers match. So indeed, p squared is equal to a cubed, because both of them equal to this number with this much accuracy. Let's, as I promised, let's look at Mars. This is the type of calculations we're expected to do in this class now. Okay, so Mars. For Mars, the semi-major axis A is equal to 1.524. I have more sig figs now. I have 4 of them. AU. But since I have to compare it to just 3, I have to really retain only 3 afterwards, because I have to compare only 3 because of the fact that the P in here has only 3. Or does it? No, it has 4 also. So now I can retain more than 3. Sorry. That 2 also have 4 sig figs. So Mars is well known then. I didn't know that, honestly. Years. So this is what I'm going to do. I'm going to do p squared, which is 1.881 times 1.881. And see what that is. I'm going to do a cubed, which is 1.524 times 1.524 times 1.524. See what that's going to give me. So I'm going to stop sharing the screen. Go back into the calculator and plug in the numbers now. So the first one is 1.881 times 1.881. Again, I only need to retain 4 significant figures now because there is too many numbers in here. So the 3, 5, 3, 8, 1. And then after that, this is 1, less than 5. So I'm going to drop that number. So in my answer, I'm going to put it 3.538. That's it, because I need to retain only 4. The same thing now for the last one, which is 1.524 times 1.524 times 1.524. I have to do the cube for the 8. And this is going to give me 3.596. The 6 now is the one that is open to debate. The 6, I have to round it up because it's more than 5. Which, if I round it up, then the 9 I have to add to it 1, becomes 10. So I have to put a 0 in here, and then the 1 from the 10 has to be carried toward the 3 to become 4. That's where I start. So the answer, according to this calculation, is 3.540. So let me stop sharing the screen. Let me share this screen. Mars, a little bit off, but not much really. Very small difference. It's actually 0. How much big difference between the two numbers? Is 0.002. So it's 0.002 of a difference between them. It's very small. As a matter of fact, if I divide it, it's less than 0.1%. So with a great confidence, I can tell you also that this is true for Mars also. This is true for Mars. So that is basically the type of calculations we're expected to do here. And this is the things, again, for the objectives for today. Let me go back into where we are supposed to be and find it. And let me share that. So again, this, oh no, I'm sorry, that's not what I'm supposed to do. I'm supposed to share the PowerPoint. The summary, the objectives. So again, this is list Kepler's 3 laws. That's exactly what we're supposed to do and carry out calculations using each of them. So basically, we did 2 examples. Part of the homework assignment is to do 2 other or 3 more examples like this. And you can work together, you can ask me, and hopefully we can do that with no difficulty whatsoever. And also the assignment today for the discussion is just to list the 3 laws of Kepler. Okay, put them, like I did them. Put them in your own words, copy them from the book, copy them from any other reference. It doesn't matter as long as you have them in there. So that is basically the unit for today and the discussion that came from it. And I know a lot of your class are not live, and that's because of the fact that we switch basically days. I know some of you guys said that they have classes today with the other classes that they have them scheduled today. And so I expect people to watch this recording and answer the prompt. And I'm going to follow up with the message for everybody that this has happened, and also for the meeting tomorrow. Sounds good? I'm going to stop the recording.